Alright, first take a minute to read the problem thoroughly. Okay, part A says, for all values between -5 and 5, find all values x for which f has a relative maximum and justify your answer. Alright, so relative mins and maxes are found on the first derivative, and if you remember, the first derivative needs to be set equal to 0 because there needs to be a horizontal tangent line, and you need to see an increasing to decreasing on the sign chart. So what we're going to do is we're talking about f, so what we're going to do is we're going to take f prime of x and set it equal to 0. Okay, well, we don't have anything that we can take a derivative of, but they gave me the graph of f prime up here. So where is f prime equal to 0? F prime is equal to 0 at x equals -5, x equals -3, x equals 1, and x equals 4. So those are my critical points on my first derivative, possible mins and maxes. Alright, now we need to figure out what sign goes where. Well, to the left of -5, this function doesn't even exist, so that really doesn't matter. In between -5 and -3, that's up here, if I were to plug in -4, I would get out +1. So that's a plus. In between -3 and +1, so now we're talking about this area right here, if I were to plug 0 into the derivative, I would get a negative number. In between 1 and 4, we're talking about the area up here, if I were to plug in 2 to the derivative, I would get out +2. If I were to plug in 5, I would get out -1. So we're looking for a relative maximum. So we're looking where the derivative goes from positive to negative. The slopes of the tangent lines go increasing to decreasing. So we see at x equals -3, it goes from positive to negative, and at x equals 4, the derivative goes from positive to negative. So that is where we have relative maximums. Part B says for all values -5 to 5, find all values of x at which the graph of f has a point of inflection and justify your answer. This is again curve sketching. Inflection points we find by taking the second derivative and setting it equal to 0 and then doing a sign chart. Well, again, we don't have the function, so all we have to do is look at the graph. I don't even have the graph of the original function. I have the graph of the derivative. So I need to take the derivative and try to figure out what the second derivative looks like. When I'm deriving graphically, I'm looking at the slopes of the tangent lines. So to say where is the second derivative equal to 0 is the same thing as saying where are the slopes of the tangent lines on the first derivative 0. So I look at the slopes of the tangent lines and I say right here at -4 there's a horizontal tangent line. So second derivative is equal to 0, or we're also looking for where it does not exist. That's going to be x equals -4. That's one of them. You'll find a second one at x equals -1. You'll see the tangent line does not exist. The second derivative does not exist because I have a sharp point here at x equals 1 and a sharp point here at x equals 2. Those 4 points are my critical points. Now I need to go on and fill in my sign chart. To the left of my first critical point at -4, these tangent lines are positive. You see positive slopes right there. In between -4 and -1, I have negative tangent lines. In between -1 and +1, I have positive tangent lines. Between +1 and +2, I have positive tangent lines. In between -2 and 5, I have negative tangent lines. I'm looking at the slopes of the tangent lines. Kind of hard to draw. The slopes of the tangent lines in between my critical points. So in order to have an inflection point, the second derivative needs to be equal to 0, does not exist, and I need to see a sign change. So what are the x values where the second derivative is equal to 0, does not exist, and has a sign change? Well, that would be x equals -4, x equals -1, and x equals 2. X equals 1 is not a inflection point because the second derivative sign doesn't change, because if you look up here, it goes positive slopes here to positive slopes here, so there's no sign change on the second derivative. The third part says, find all intervals on which the graph of f is concave up and also has a positive slope. Explain your reasoning. So concave up and positive slope. So you think about concavity. Concavity was the second derivative. If it's concave up, that means the second derivative is positive. If f has a positive slope, that means that the first derivative is positive. And that's where you think to yourself, all right, I've already done all this work. If I go back to parts A and B, I already have my sign charts done. So I look at my sign charts, and I'm trying to find where the first derivative is positive and the second derivative is positive at the same time. Well, the first derivative is positive from 5 to -3, but the second derivative is positive only from 5 to -4. So they are both positive, starting at -5, going to -4. The second derivative, you see, is negative all the way to -1, so that can't be the answer. When I pick up at -1, well, unfortunately, the first derivative is now negative all the way to +1. At +1, the first derivative is positive, the second derivative is positive. That stays the case all the way until x equals -2. At x equals -2, the second derivative turns negative. So they are both positive from x equals 1 to x equals 2. Okay, part D says, find the absolute minimum value of f of x over the closed interval -5 to +5. Explain your reasoning. Well, absolute mins and maxes, again, if you remember absolute mins and maxes, we have to take the first derivative, set it equal to 0, find a sign chart to find my relative mins and maxes. Again, we've already done that in a previous part. So you see that the derivative goes negative to positive at x equals 1. That means that the function f of x goes decreasing to increasing at x equals 1. So that means there's a relative min at x equals 1. So then I need to figure out, I take f of 1, and they tell me in the problem that f of 1 is equal to 3. Now that's a relative min. How do I tell whether it's a relative min is an absolute min? Well, I need to compare it to the endpoints, which means I need to figure out what is f of -5 and what is f of 5. In order to do that, I need to do some geometry with the picture above. To find f of -5, I would need to create an equation. F of -5 is equal to the 3, which is the y value I know for f of -1. I would need to add to that the integral between 1 and -5 of f prime of x dx. Well, you notice there's something fishy about those limits of integration. It's integrating from right to left or backwards. And we don't really know how to do that. We know that that's the thing that sort of sets off that alarm bell. We know we can flip those limits of integration if I flip the sign. And now I'm doing the integral right. So I just do area under the curve using geometry, and I find that f of -5 is equal to 3 minus the quantity. The first circle is going to be half of a circle, which is 1/2 pi r squared, r being 1, so I just get pi over 2, plus the second circle, which is going to be, again, 1/2 pi r squared, r being 2, gives me 2 pi, but this is area under the curve, so it's negative. So that's going to give me 3 minus pi over 2 plus 2 pi, which is obviously greater than 3. So that endpoint is now ruled out. When I do f of 5, that's going to be 3 plus the integral from 1 to 5 of f prime of x dx, exact same concept. So when I'm evaluating that integral, I have 3 plus, now it's a lot easier because all I'm talking about is triangles. If I look up here at the picture, this base is 3, this height is 2, 1/2 base times height. The area of that triangle is going to be positive 3. And then I've got this little baby triangle right here with base of 1 and height of 1. It's below the x-axis, so that's going to be plus a negative 1/2. So that is also obviously going to be greater than 3. I can conclude that the absolute minimum is at f of negative 1 equals 3.